here the whole week. And from August 1, he will be here for however long I can keep him. Yeah, Robert has been doing amazing work in algebraic complexity. He got like the best student paper award in a Fox 22. Yes. And ever since then, he has been doing some really cool work. And today he's going to tell us about constant depth arithmetic circuits for a lot of cool linear algebra problems.
All right, yeah, thanks, Raphael, for the introduction, and thanks everyone for packing in here. Hopefully this will be, a friendly, accessible talk. If you have questions, just ask. So what I'm going to, so everything I'm speaking about is joint work with Avi Wigderson, who's also at the IAS. And hopefully I can tell you about some cool results today. So we're going to speak about a problem that we all remember from kindergarten, but maybe it's been a while since we've thought about it. We're going to look at greatest common divisors of polynomials. So just as, a reminder, a refresher, throughout the talk, we'll have two polynomials, f and g. These are univariate polynomials. They take coefficients in some field f. You can think of this as the complex numbers. And we want to compute their greatest common divisor. This is just the highest degree polynomial that is a divisor of f and is a divisor of g. And so, it's the middle of the week, so maybe your coffee is kicked in, you're in the working mode, but just as a reminder, say I have two polynomials here, f and g, and I've written them, I've factored them. F has some factor, say x minus a with a square, and some factor x minus b with a power 5, and g has the same factors, but with different multiplicities. What the GCD does is it just takes, for each factor, you take the minimum multiplicity you see in each polynomial. Now, of course, this is, a way to sort of mathematically define the GCD. To compute it, this suggests that maybe you need to factor the polynomials, but of course we know you can compute GCDs without factoring. And in fact, we've known for quite a while how to do this. So, so the question in this talk really is we want to understand the complexity of computing the GCD. How many arithmetic operations do we need? So if you're thinking of the complex numbers as, the ambient field you're working in, I can do complex arithmetic at unit cost. I'm not counting bit complexity, I'm just counting additions and multiplications. And why would you want to compute the GCD? I mean, this is just a fundamental problem in computer algebra. It's just, as natural as adding or multiplying numbers, adding and multiplying polynomials, but it also has nice applications to problems in polynomial factorization. It has applications to coding theory. This is a very basic fundamental thing that we want to compute. So what do we know? Well, so we know that you can actually compute the GCD in polynomial time, and you can do this at least on its face without any kind of factorization, right? This is the Euclidean algorithm. It's a polynomial time algorithm. Let me remind you what this algorithm does. So you start with f and g, and what you're going to do is you're going to compute a sequence of remainders. So in the very first step, you take the remainder of f when you divide it by g. You write that down as some remainder R2. Now you take g, divide it by whatever that remainder R2 was, you get some new remainder R3, and you keep doing this division with remainder. Every time you do this, the degree of your polynomials goes down. So this will terminate after, at most, d loops. And each division with remainder, you can implement, say, in quadratic number of arithmetic operations. You can be smarter about how you do this, get something like each division with remainder in quasi-linear time. So you can, of course, do better than this. And in fact, there are very clever algorithms that do some kind of divide and conquer on top of the Euclidean algorithm. And if you're really, really clever, you can compute the GCD in a near linear number of arithmetic operations. Okay, so this is a problem that you can solve really very easily. You can solve it very quickly. So why am I talking to you about this? This is work that's 50 years old. The question that I want to talk about today is really, can we design parallel algorithms to compute the GCD? This Euclidean algorithm thing, you're computing this sequence of remainders. And it seems like, why can you avoid computing this sort of sequential thing, right? The very last remainder in that sequence, which is the GCD, it seems like it depends on everything you previously computed. Why could you speed this up? Why could you do this in parallel? Also, these fast versions of the Euclidean algorithm, they're also seem like they're inherently sequential. So why could you hope to do anything in parallel at all? And the reason you can do something, well, I mean, you can actually do better. You can compute GCDs in something like polylogarithmic parallel time. So this is a result by Borden, von Zergatten, and Hopcroft from about 40 years ago that says, in fact, okay, I'll use a polynomial number of arithmetic operations. Let's not be so concerned about the number of operations, keep it polynomial. And you can actually solve this problem in polylogarithmic parallel time, which is kind of amazing, because it seems like it's completely bypassing the Euclidean algorithm, and it is. It's using some different idea. So what's the idea? How can you compute the GCD fast in parallel? Well, you're going to use linear algebra. You can express the task of computing the GCD as a system of linear equations. And once you do that, you can just invoke in a black box manner parallel algorithms for linear algebra. And I should say, this is something that you can only do, well, it seems like you can only do for the GCD of polynomials. If you want to compute the GCD of integers, we don't know any parallel algorithms. And in fact, we suspect that this is a problem that's inherently sequential. So let me tell you about this reduction to linear algebra. How can you write the GCD in terms of linear algebra? And in fact, I'm going to show you an even simpler version of the problem. I just want to test if the GCD is 1. I want to test polynomials for coprimality. So what does this look like? So we'll have two polynomials, f and g. The fi's are the coefficients of f, and the gi's are the coefficients of g. So those are our inputs to the problem. And there's a fact that the GCD is 1. These polynomials are coprime. If and only if, well, something happens, right? And what is this condition? What is this something? You can find two polynomials s and t of low degree. So the degree of s is less than the degree of g. The degree of t is less than the degree of f. And you have a polynomial identity. S times f plus t times g, this should be identically 1. Now, why is this interesting? Well, once you have these degree bounds on s and t, this is really a system of linear equations. Your unknowns are the coefficients of s and t. And the knowns are the coefficients of f and g. So this is some system of linear equations. You could try to solve this. And in fact, this system has some special structure. In fact, this solution exists if and only if the system is invertible. So you just need to look at a particular matrix and look at its determinant. And this is what this determinant looks like. You have some parallelogram where you've arranged the coefficients of f and some parallelogram where you've arranged the coefficients of g. And you want to test if this determinant is 0 or non-zero. When it's non-zero, these polynomials are coprime. When this determinant is 0, they have a common factor. And this is some quantity that's been studied for well over 100 years. It's called the resultant of f and g. So if you've never heard this term before, this is a really cool function of their coefficients, and we'll see this later. But the point is, you can even just test coprimality by evaluating some determinant. And of course, this is some very particularly structured determinant, so maybe you can, in fact, take advantage of that structure, but okay, let's not even try to be clever. What can we do already? So I'm just erasing some of the context here. Really, we have two polynomials, and we just want to compute some determinant, which is defined from their coefficients. Well, it turns out that you can take any n by n determinant and compute it in something like log n squared parallel time. And not only, so this already gives you a fast parallel algorithm to compute the GCD. Well, not compute the GCD, test coprimality. You can, of course, extend this idea to actually get an algorithm that's parallel and computes GCDs. But the question here is, well, can we do better? Right? If you're not familiar with this sort of log squared parallel time, this log squared depth, there's reason to believe that you can't do better than this for general linear algebra. That if you want to compute a determinant or invert a matrix, you really do need to pay this log squared. So we're going to try and get around this and maybe use the special structure in this linear system, in this determinant, to try and do better. So before I move on and start telling you about algorithms, I want to just open up, I have some word here, algebraic circuit. I want to explain what that is because that's the model of computation I want to work with in the talk. Okay, so what are algebraic circuits? This is just one slide of definition, bear with me. These are circuits that are built from addition and multiplication gates. They take as input formal variables, and they output a polynomial, over your field, and it's sort of this natural definition where an addition gate computes the sum of whatever its inputs are, and product gates compute, well, the product of their inputs. So this circuit, well, this gate computes x plus y. This gate computes x minus y. And this gate computes their product, which is x squared minus y squared. And there are two parameters of these circuits we'll be interested in. One is the size, which is just the number of gates in the circuit. And the other is the depth, which is the longest distance from any input to an output of the circuit. And this depth is really our measure of parallel time in this talk. Because what I can do is, at every layer of the circuit, I can evaluate all the gates in one layer at the same time in parallel. So if I have a low depth circuit, this corresponds to a fast parallel algorithm. So really, these algorithms for computing determinants in parallel, solving linear systems, they can be expressed as an algebraic circuit of log squared depth. Okay, so that's it for context. So what am I going to tell you about? So what were we able to do? So we were able to improve on these classic algorithms for the GCD and related problems. The classic algorithms run in log squared parallel time or log squared depth, and we'll get something better. So for degree D polynomials, we can compute the resultant. So this is this quantity that tests coprimality. We can compute the GCD itself. We can compute these two polynomials, S and T, that witness the GCD, and also something called the square-free decomposition of F and G. If you don't know what this is some kind of structured partial factorization of these polynomials. And we can do this all with algebraic circuits of polynomial size and constant depth. So when I say constant depth, I really do mean the depth of the circuit is constant, but gates can have large fan-in. So if you really implement this on a computer, you'll get log parallel time, not log squared. But I should mention that we get constant depth circuits of polynomial size. It's known unconditionally that constant depth circuits of polynomial size cannot compute determinants. So there's some unconditional separation between linear algebra and these problems around the GCD. Testing coprimality, finding these S and T, all of this is somehow different. It's easier than generic linear algebra. Okay.
Can I ask something?
Yeah.
Do you know what this O1 is? Is it like 5 or 100?
For the resultant, it's maybe 11 or 12. And it's at most a 2-digit number, but we didn't bother to check. I think I'll hedge and I'll say definitely at most 20, but I'd have to get back to you on a more precise number. Okay. So my goal today is to tell you how to compute the resultant in this low depth. So that was the structured determinant on about 2 slides ago. And then some special case of the GCD, which is maybe not so special, but we'll do a special case just to keep notation minimal and really focus on the ideas. All right. So what I want to tell you about now is, let's forget about the GCD for a second. We're losing linear algebra by going to constant depth. So what kinds of algorithms can we implement with a constant depth circuit? What kinds of computations do we even have to work with? So the first tool that we're going to use is polynomial interpolation. Okay, so I just want to build our toolbox a bit. So what are we doing? So we'll have some, say, multivariate polynomial f, and I'm going to single out one of the variables from the others. And you can always take a polynomial in many variables write it as a polynomial in a single variable whose coefficients are polynomials in the remaining variables. Okay, now you might ask, well, if I can efficiently compute this polynomial f, could I extract these coefficients fi? And that turns out to be true. So if you can compute this whole thing, this f, in size s and depth delta, so here you should think s is something polynomial and depth delta is maybe a constant, maybe 10, 20, 30, your favorite number, then you can compute each of these coefficients, each of these fi's, in size order, s times d. So d was the degree here, and depth delta plus 1. So what is this saying? This is saying that I can extract these coefficients. I pay a mild blow up in the circuit size. It's not too big. And I'm really careful about the depth. I'm only increasing the depth by an additive 1. So in particular, if I had a very, very low depth circuit for the whole polynomial, this whole f, then I get low depth circuits for each fi. And how does this work? This is just polynomial interpolation. Okay, so what exactly do I mean by this? Well, suppose you put in, you plug in different values of y here. You plug in 0, 1, 2, 3, 4, and so on. Right? Polynomial interpolation says I can take those evaluations and write each coefficient as a linear combination of the evaluations. Right? So here, how you should read this is, here for f, we have a small low-depth circuit. We're copying it d times, and we're adding one layer of depth to implement this linear combination. That's it. So this is the first tool we'll use. Let me give you some idea of how you can even use this. Where is this going to be useful? What can you do with this? Because this seems like a very basic, I'm not telling you anything yet. So let me tell you something a little more interesting. So I want to look at this example of this family of polynomials called the elementary symmetric polynomials. These are like some kind of algebraic version of maybe a threshold function, if you're familiar with that. Okay. So what are these? These are parameterized by two numbers. So we have n, which is our number of variables. We have some degree d. And what we're going to do is, well, this polynomial is going to sum over all subsets of d variables. And for each subset, you pick up the monomial, which is the product of those d variables. Okay. Now, why would you even care about these polynomials to begin with? Well, these are actually going to be a central player in the rest of the talk. So one reason you might care about these is these are fundamental in the study of symmetric polynomials. So a polynomial is symmetric if I can permute the variables around and I get back exactly the same polynomial. And why would you care about these? Well, I mean, we'll see why we care about these, but the elementary symmetric functions really are elementary. They're very important here in the following sense. So for every symmetric polynomial f, you can find some polynomial g. It may not be symmetric, such that f equals g composed with the elementary symmetric functions. So this is saying for every symmetric polynomial, you can explain the fact that it's symmetric by writing it in terms of the elementary symmetric functions. That's what this says. The other reason you might care about these functions is suppose you have a univariate polynomial over the complex numbers. You can always factor it into linear terms. And if you know this factorization, well, of course, you can expand this factorization and write f as a sum of powers of x. What are the coefficients of f? Well, up to a sign, they're the elementary symmetric functions of the roots. So when I give you the coefficients of a polynomial as input, you should really think of this as I'm giving you the elementary symmetric functions evaluated at the roots of the polynomial. So I haven't given you the roots, I haven't given you the factorization, but I've given you some information related to it. Okay. So now here's a really surprising result. So for every elementary symmetric polynomial, you can actually compute them in depth 3 and quadratic size. And this is surprising if you've never seen this before. This is like the only way that you would maybe think to compute this in really low depth is just to sum over all the monomials. And that has like size n choose d. That's way too big. So how can you get polynomial size? Well, this is a nice application of interpolation. So look at this polynomial, 1 plus y times xi, and you take the product over I from 1 to n. So here each xi is a variable and also y is a variable. Expand this out. As a polynomial in y, its coefficients are exactly the elementary symmetric functions. So now you apply interpolation that I showed you a few slides ago. You can take linear combinations of evaluations of this polynomial and get back the elementary symmetric functions. So you can compute these in quadratic size and in low depth. That's one application of interpolation. This gives you a sense of what you can do with it. What else can we do with interpolation? Well, we're going to look at another family of polynomials, which will also play a really important role in what we're doing. We're going to look at these things called the power sum polynomials. This is maybe a simpler looking family of polynomials. I have n variables, and I just take the sum of their dth powers. Now you'll notice this is also a symmetric polynomial, just like the ones from before. Right? If I permute around the xi's, it doesn't actually change this polynomial. And you have another theorem that says these are also foundational in the study of symmetric polynomials. So here, again, for every symmetric function f, I can find some polynomial g, not necessarily symmetric, so that f is g composed with these power sum polynomials. Now here, if you're familiar with this, this has some maybe assumptions on the field. Let's not worry too much about that. But the point is, this hints that, okay, there's some kind of conversion that we can do between the elementary symmetric functions and the power sums, right? Each elementary symmetric function is symmetric. So this says that you can write them in terms of the power sums and the other way around. So can we actually make this conversion explicit? And we'll see that doing this conversion explicitly in low depth, this is going to be our second tool. And then once we have that, all the algorithms will just start coming for free. So we really need to understand how this conversion looks. Okay. So, this is not something new. This was understood by Newton, in fact, in the 18th century. And you can write down some explicit identity that relates the power sums and the elementary symmetric polynomials. Now, the way you should read this is, suppose you have the evaluations of the elementary symmetric. You just have the elementary symmetric polynomials in your hand, and you want to write down the power sum polynomials. Well, you would start with P1. Well, that's really the same as E1. So now you want to write down P2, the degree 2 power sum. Well, if you think of D as 2, you have P2 here. E2, you have this in your hand. And then this sum will involve E1 and P1. You also have those in your hand. So now you can write down P2. Next, you want to write down P3. Okay, so you have P3. You have E3. You have that in your hand. And then this sum involves E1, E2, P1, and P2. You have all of those in your hand, so you can get P3. You get an iterative algorithm that will let you convert between these. We want a low-depth algorithm. How could we do this kind of conversion in low depth? Well, there's sort of a nice compact form of this identity that somehow is maybe expressing this same identity for all values of D simultaneously. So I need a little bit of notation here. So I want to look at the power series of the exponential function. And it's a fact that you can go check in the privacy of your own home. Let's not do it here. That if you write down the generating function of the elementary symmetric polynomials, this is equivalent to some exponential function applied to something which looks like the generating function of the power sum polynomials. So that's nice. This is something different, some different way of representing this. But I mean, how does this give us any kind of algorithm? I mean, here you have two infinite objects, right? This inner function is some infinitely long power series. And then applying the exponential, it's also some infinite object. So I want a finite algorithm. What are we going to do? So first, we're going to just move this up to the top of the slide. And we want to understand this identity a little better. So the idea is, well, here you have some object up to degree n. So you could imagine if I implement both of these infinite pieces really only up to degree n, up to some precision n, then I get something which is correct to precision n, and then there's some junk after that. And so that's actually what we're going to do. So if you take the exponential and you truncate it up to degree n, and then you truncate this inner series up to degree n, what do you get? This is some finite object. And if you expand this out, you get, well, on the right-hand side, you get the elementary symmetrics up to degree n, which is exactly what you want. And then you have some higher degree junk terms. Okay, so this is some finite identity that's now relating the power sums and the elementary symmetric polynomials. How can we get an algorithm out of this? So I'm just taking the identity, moving it up on the slide for more space. And now here's one thing we can do. Suppose we're given as input the power sums. I claim that from those, we can compute the elementary symmetric functions in polynomial size and in constant depth. And how do you do this? Well, you're going to apply interpolation to this identity here. We have the power sums as input. So, I mean, what is this function on the inside of the exponential? This is some constant depth expression in terms of the power sums. And then truncated exponential, that's also some constant depth expression. So we get some constant depth circuit, which computes this generating function on the right. It's correct up to degree n, there's some junk above that, but you can apply interpolation and you get these coefficients, and you get them correct. And the other way around, if you're given as input the elementary symmetric functions, you can convert to the power sums in constant depth and in polynomial size. And here, when you do this, you can actually convert to the power sums in a way where the elementary symmetric functions, they stop at degree n, right? There are no subsets of n elements where the subset has size n plus 1. So they stop at degree n. On the other hand, the power sums are defined in all degrees. And when you work out the details, you can really take the power sums up to whatever degree you like. And that will turn out to be important later on. Okay, so we have this conversion between...
Just to be sure, so let's say that the first version there, you're interpolating something of degree n square, right?
Yes, yes, yes. And here you'll also do something like at least up to degree m at least, or something. Maybe m times n, I don't remember. Yep. Yeah, okay. So what can we do with this? I mean, this is some interesting algorithm, but I mean, it's not clear that you get anything out of this yet. So let me give you a toy example that at least convinces you there's something to be used with these. So I want to look at division of polynomials, but I'm going to look at a promised version of the problem. So here we're given two polynomials, f and g, and I promise you that g genuinely divides f. Please compute their quotient. And I want you to do this in constant depth. I don't want you to actually do polynomial long division. This is some very deep computation potentially. So how would you do this? Well, let me give you a simple algorithm. Okay, so let's say for the sake of analysis, we can't actually do this algorithmically, but for the analysis, let's factor f and g as products of linear terms. Because g divides f, we know it looks like this, that there's some set of roots that f and g share, and then f has some extra terms here. So what are we going to do? So remember, the coefficients of f are the elementary symmetric functions evaluated at its roots. And the coefficients of g are the elementary symmetric functions of its roots, up to a sign, but we can figure out the sign, so forget the sign. So we have the elementary symmetric functions of alpha and beta together, and we have the elementary symmetric functions of alpha alone, and we want to get beta alone. We want to remove the alphas from this guy, right, from the collection. So what do? Well, using these Newton identities in constant depth, I can compute the power sums of alpha and beta together. This comes from the coefficients of f. And again, in constant depth, you can compute the power sums of just the alphas. These are from the coefficients of g. Now, you use subtraction. You get the power sums in just the betas alone. Now you use Newton's identities again to get the elementary symmetric functions of the betas, which are exactly the coefficients of the quotient f divided by g. So you can do this polynomial division in constant depth, at least when one polynomial is promised to divide another. Now, it turns out we're not the first people to look at this. In fact, constant depth polynomial division has been known since the 80s from work by Bini and Pan. They didn't phrase it this way, but if you look at their algorithm, it can be expressed in constant depth. They also handle division with remainder, so this is not new. But this is meant to illustrate why these identities are even useful. How can you get an algorithm out of them to begin with? Okay, so now let me show you. Is there a question? No, okay. So let me show you another application of these, and I promise we're making progress towards these questions about the GCD. I promise you. So here's another problem that we can solve. So this is starting to be new stuff. So say I give you the coefficients of f and g, and I ask you to compute this quantity. So the roots of f are these alphas, and I want you to evaluate g at each root of f and give me the sum of these evaluations. Of course, you could try to say factor f and then compute each of these values explicitly and sum them up. I want you to do this in constant depth in a very, very fast parallel manner. How can you do this? Well, let me just show you. Okay, so what we're going to do is first, from the coefficients of f, we can compute all the power sums of the alphas. Right? This is this Newton identity trick again. We're doing this in constant depth. And then take this sum, expand it out, and change the order of summation. What is this really? This sum is something like an inner product between two vectors. The first vector is the coefficients of G, and the second, well, it's the vector of power sums in the alphas. We have both of these, so we can just compute the inner product in constant depth. Okay, so this is a nice trick. It's not exactly clear what can you do with this? Like, why would you want to compute this quantity? And I don't have a good answer for that. But we can use this to compute something related, which will be more useful for us. So here, I'm going to change what function of the G alphas I'm going to compute. So we're going to do the same thing, but now we'll compute some elementary symmetric function evaluated at the G alpha i's. And again, we'll do this in polynomial size and in constant depth. How would you do this? So on the previous slide, you had E1. You had the sum of the G alphas. Now what are we going to do? Well, first what you can do is in constant depth, you can interpolate out the coefficients of powers of G. Right? I can write a constant depth circuit that computes a power of G, so then I can interpolate out all the coefficients. Using the trick on the previous slide, you can compute these sums of powers of the G alpha i's. I have a power sum in these objects. I have many different power sums in these objects. So now I can use the Newton identities again to convert back to the elementary symmetric functions. And every one of these steps was done in constant depth and polynomial size. So the overall algorithm is constant depth, polynomial size. Now, okay, it seemed like I'm just generalizing for the sake of generalizing. I have a nice trick. I can do something more with it. Why would you want to do this? So this is giving us something interesting. So let's go back to this quantity I spoke about earlier, the resultant of two polynomials. Right? This was some quantity that tests for coprimality. The two polynomials are coprime exactly when this resultant thing is non-zero. Well, okay, one definition of the resultant is this funny looking determinant. You take the coefficients, you arrange them in parallelograms. There's another way to express the resultant, which is, it turns out that if f has these roots alpha I, the resultant is exactly the product of the G alpha i's. Up to, something that involves maybe a sign, up to something involving the leading terms of f and g. Let's not worry about those details, but you can worry about them later on if you care so much. The point is, well, this is an elementary symmetric function of the G alpha i's. It's the degree n elementary symmetric function of these G alpha i's. I showed you on the previous slide how to compute this in polynomial size and in constant depth. So as a nice corollary, we get a constant depth circuit to compute the resultant. And up until this, at least we didn't know anything better than this, generic linear algebra approach of computing the resultant with respect to depth. So that gives us something nice. Why would you want to compute this? Okay, this tells you something about coprimality. There's also a nice application of this. So there's a related quantity called the discriminant, which is just a function of one polynomial. It tells you if this polynomial has a double root. And it turns out that, a polynomial has a double root exactly if this discriminant is 0. This is really just the resultant of f and its derivative. Okay, so, this is sort of not saying anything. I just showed you how we can compute resultants. So we can compute discriminants in constant depth and in polynomial size. And you've seen this before, even if you don't know it by this name, because if you take a quadratic polynomial and you take its discriminant, it's exactly this b squared minus 4ac that you've seen in the quadratic formula. That tells you if you have a double root or if you have two different roots. Okay, so this is at least giving us some hope that we can do, something with the GCD in very low depth. Now let me actually move to something with the GCD. So I'm going to show you how to compute the GCD of what are called square-free polynomials in constant depth and in polynomial size. So here, throughout this part of the talk, f is a polynomial whose roots are these alpha i's and gamma i's, and g is a polynomial whose roots are these beta i's and gamma i's. And what I mean by square free is that every alpha, every beta, every gamma, these are all distinct numbers. Okay? If two quantities have a different symbol, they are different numbers. And we want the GCD, which is exactly the product of the x minus gamma i's. That's what we want. Okay, so in order to compute the GCD, you have to let me do one clever thing. So I apologize for having to do something clever in a talk, but I'm going to look at this polynomial in two variables. It's z minus x times g of x. And what I want to do is I want to look at how does this polynomial behave when I plug the roots of f into the variable x. So what happens? Well, so say I put alpha 1 into x and call this, say, some lambda 1, right? This is some polynomial in the variable z. Well, it's z minus alpha 1 times g of alpha 1. Now, the alphas are not roots of g, so this is some non-zero polynomial. And you can do this for all the alphas, and all of these values are non-zero, because these alphas are genuinely not roots of g. Now, what about when I plug the gammas in? Well, the gammas are shared roots between f and g, so I get something 0. And I get 0 for all the gammas. So, big picture, what I'd like to do is I'd like to take something like the product of just these first n values. If I were to get the product of these guys, well, that would be something like f divided by the GCD. Okay, I can fix things up after that. The problem is we know, how many common roots there are for the purpose of analysis. But of course, this is an algorithm. The algorithm doesn't know this. So what are we going to do? So let's take all of this, shrink it down to here, just to give myself more space. So what I want to do is I want to look at what the elementary symmetric functions of these lambdas, what happens? How do these behave? Because we know we can compute these. Even though the algorithm I showed you earlier just evaluated some univariate polynomial at the roots of f, I can do this with a bivariate polynomial at the roots of f. So the point is I can compute these values in constant depth and in polynomial size. What do they tell us? Well, if you expand out this sum, every monomial that you get in this summation, well, it has some terms from the first n of these lambdas. And if you remember the first n, these are non-zero. These correspond to the roots that only belong to f. And then from the remaining d, well, we get some lambdas, which those come from the common roots. Now, if from this last d set of roots, we pick up any of these lambdas, that gives you a 0. So that term will vanish. So in fact, this summation, anytime this t is non-empty, we get a 0 term. So this simplifies. We're only taking an elementary symmetric function. It's of the same degree, but only on the first n of these values. Right? So really, all the 0 values drop out from these symmetric functions. That's the point here. Now, actually, we know everything we need to compute the GCD. I just need to rearrange things a little bit and clean it up. Okay, so here's the thing. Suppose we knew what n was. Suppose we knew the degree or the number of roots that f has that are not common with g. Well, if we knew that, what is this elementary symmetric function? It's just the product of z minus alpha I times g alpha I. Right? These are some scalars. Okay, so normalize this polynomial to have leading coefficient 1. This is f divided by the GCD. So you can compute this in constant depth, and then use the algorithm I showed you for division to just divide f by this, you get the GCD. Okay, so what's the algorithm here? So I give you two polynomials f and g, and we're going to compute their GCD, and these polynomials are square free. So all the roots just have multiplicity 1. So what do we do? So first, I'm going to compute all of these elementary symmetric functions of the lambdas. So remember, that just says I take this bivariate polynomial, and I take I plug the roots of f into x, and I take elementary symmetric functions of that. We can do that in polynomial size and in constant depth. And then what I need to do, this is one operation that unfortunately doesn't actually fit in this model of arithmetic circuits. I need to look at all these evaluations and find the largest one which is not 0. Now, why do I want the largest one that's not 0? Well, certainly the degree n elementary symmetric function, n is the number of factors that f does not have in common with g. That gives you f divided by the GCD. What if you take higher degree functions? Well, you'll have to pick up some of these zeros in every term of your symmetric function. So you'll always get 0. So the very top degree guy, it's 0, 0, 0, 0. And the first non-zero one you see, this gives you enough information to get the GCD. Okay, so you normalize this to have leading coefficient 1, and you output this quotient as the GCD of f and g. Well, that's it. That's how you get the GCD of square-free polynomials. And it turns out that a pair of random polynomials, they'll be square-free. So this is like, on almost all inputs, we can get the GCD correct.
But then the GCD would be 1 too.
Yeah, exactly. The GCD would be 1. So to handle multiplicities, I need to do some tricks looking at derivatives here to take multiplicities into account. I won't show you that here, but let me just end by telling you a little bit more general thing that we are somehow able to do. That seems strange. Okay, so here's something general. So we have f and g, and I'm going to change notation just a tiny bit here. Now the roots I'm going to write as these ri's, and the ri's are the union of the set of roots. So there might be some terms here in f that have multiplicity 0. There might be some in g that have multiplicity 0. Okay. Now, the GCD is really for each root ri, you take it with multiplicity, which is the minimum of ai and bi. So what other functions could you put here? If you put addition, that's like multiplying polynomials. If you put subtraction, it's kind of like dividing. So what else could you put? Could you do something, could you do something silly, like I put the products of ai and bi, right? I don't know what that means, but you could certainly ask, can you compute this? Right? Can you even compute it, and can you compute it efficiently? And it turns out we can. I don't know what to do with it, but in fact, you can put any function defined on natural numbers here, and you can compute that in, well, constant depth and polynomial size, where the polynomial is polynomial in the size of the input and polynomial in the size of the output. You could be really evil and pick a function that makes me write down a gigantic polynomial on very small inputs. So of course I have to pay polynomial in the size of the output just to write it down. But so we can do this in small size and in constant depth, and we don't really know what are good uses for this, right? Like, what does this scalar product even mean in the exponents? Can you do something with this? I'd love to know. Yeah, that's it. Thanks all for your time.
All right, does anybody else have any questions for Robert?
You mentioned that for integers, it seems like the situation is much more inherently sequential.
Mhm.
Is there any intuition for why this should be the case?
Smarter people than I have thought about it, and they seem to think that it's sequential, but I don't have any good explanation for it.
Mhm.
Yeah, I think the only explanation I could come up with is you don't have this nice linear algebraic rephrasing of the problem for integers. And using linear algebra seems like really like one of the key ways we can get parallel algorithms for the polynomial version of the problem.
Mhm.
Yeah.
More questions?
So what if you have lots of polynomials you want to take GCD on?
Yeah, you can do that in polynomial size and in constant depth.
And what if it's super constantly many polynomials even then?
Yeah, yeah,
Okay.
as many polynomials as you like.
Do we study the coefficient growth as well in your algorithms?
You could, we didn't,
I see.
but you could.
I see.
More questions?
That's fine.
Okay,
You know how to find me.
Yeah.
yeah, if you have more questions, Robert will be here until
Yeah.
the end of the week,
And then I'll be back in August for a little while.
a little while. All right, thank you very much.
All right, thank you, Bill.
So.